If your model trains forever, it's usually the optimizer. Atom versus SGD on the same problem. No hand-waving. By the end, you will understand what each optimizer actually does, when one wins, and how to spot the trade-offs in a small Python experiment. I'm Professor Pi, teaching AI foundations with simple Python. Training neural nets is mostly about making the right updates to weights. Optimizers are the rules that turn gradients into parameter changes. People pick Atom because it looks fast and needs less tuning. They pick stochastic gradient descent because it often gives better final accuracy and simpler generalization. In practice, success means lower validation error and stable training on your dataset size. For tiny regression tasks, this shows up as mean squared error on held-out data. For larger vision models, it shows up as accuracy or loss curves over many epochs. Start with the intuitive idea. SGD moves straight down the slope using the current gradient. Atom adapts each parameter step size using running averages of past gradients and squared gradients. SGD with momentum remembers direction and smooths updates. Atom can be fast early, but SGD often matches or beats it with the right learning rate or momentum. Think of Atom as an adaptive bicycle gearing system, and SGD as pedaling at a steady cadence with wind resistance handled by momentum. We will build a tiny regression example in PyTorch, measure a baseline loss, then train the same simple net with SGD, with Atom, and with SGD plus momentum. And finally, evaluate on held-out noise to compare generalization. No complex datasets, just a linear relation with noise, so you can see optimizer behavior clearly. Next, we measure the initial baseline loss before any training. This snippet measures a baseline regression loss in PyTorch before any training. It first sets a seed to keep results stable, then creates the input tensor X and a noisy target Y from a simple line. The variable M is a tiny neural net built with nn.Sequential and a single nn linear layer. The expression m of x minus y squared, averaged with mean, computes mean squared error without defining a separate loss object. Finally, the code prints the initial loss, so you know where optimization will start. A higher number here means more work is needed to fit the data. Now we train that tiny net with plain SGD and watch the final training loss. This example trains the same toy model using PyTorch Optim SGD. It recedes for repeatable initialization, constructs a fresh nn sequential with one nn linear layer, and attaches an SGD optimizer with a learning rate stored in LR. Inside the loop, zero grad clears old gradients. The mean of squared errors computes the loss. Backward populates gradients, and step updates weights. The print uses an assignment expression to store the final SGD loss and display it. Increasing LR speeds convergence, but risks overshooting and divergence. Decreasing LR is safer, but slower. A substantially lower SGD loss than the baseline confirms progress from gradient descent. Next, we repeat training with Atom and compare its result to the SGD run. This code runs PyTorch Atom on a fresh model and compares its final loss to the earlier SGD result. A new non-sequential linear model A is created with the same seed, and Atom is configured with a moderate learning rate and betas that control first and second moment averaging. Each iteration zeros gradients, computes mean squared error, backpropagates, and updates parameters via Atom's adaptive steps. The code then prints loss gap, which is Atom's loss minus SGD loss from the prior snippet. Lowering LR or beta 1 can slow convergence. Higher values may speed it, but risk instability. A negative gap means Adam converged better here. Now we try to match Adam's behavior by adding momentum to SGD. This snippet shows how PyTorch's SGD with momentum can close the gap without switching optimizers. A new nn.Sequential linear model, MS, is created with the same seed, and Optim SGD is configured with LR and momentum to accumulate velocity from past gradients. Each step zeros gradients, computes mean squared error, backpropagates, and updates parameters with momentum smoothing the direction of travel. The print reports momentum gain as the reduction versus the plane SGD loss, increasing momentum towards 0.9 to 0.99, usually accelerates along consistent directions, but can overshoot. Decreasing it behaves more like vanilla SGD. A positive gain indicates momentum helped training. Finally, we test which trained model actually generalizes on fresh, noisy data. This example evaluates generalization by comparing PyTorch models on held-out data. It creates a validation input XV and target YV with fresh noise for a fair test. The variable LA computes mean squared error for the Adam-trained model A, while LM measures the momentum SGD model MS. The print selects best based on which validation loss is smaller, and reports the corresponding MSE. If you expand the validation range or reduce noise, differences may shrink. With more noise, regularized methods can win. A lower reported MSE for one optimizer shows it not only trained fast, but also generalized better here. In a real project, this toy maps to a quick experiment you run before scaling. Replace the linear data with a small subset of your real dataset and run the same sequence to see which optimizer and hyperparameters are worth scaling up. Recap what it is. Adam is an adaptive optimizer that uses running averages of gradients and squared gradients. SGD is the basic gradient step, and momentum adds velocity smoothing. When to use it? Use Adam for quick experiments and when tuning budget is tiny. Use SGD with tuned learning rate or momentum for final training when generalization matters. One caveat: Adam can converge fast, but sometimes yields worse validation performance on bigger tasks unless regularized or tuned. Next step: tune the learning rate for each optimizer and plot validation loss curves to compare convergence and generalization directly. If AI Foundations in Python help, subscribe and watch the AI Foundations videos.